So for this question, we need to use the Poisson equation. And this simply says that the volume flow rate is equal to the the difference in pressure needed to maintain this volume flow rate times the radius to the fourth power divided by 8 over pi times the viscosity of this liquid times the length. Now, the only thing that is changing is the radius. And because the only thing that's changing is the radius, and we need to find the pressure, and the volume flow rate is staying constant, the volume flow rate itself doesn't matter. We can actually simply just create a relationship and say that the change in pressure in the first section times the radius in the first section to the fourth power equals the change in pressure needed for the second section times the radius in the second section to the fourth power. Again, the viscosity, the length, 8 over pi is a constant, volumetric flow rates, all of these are constants. The only thing that is changing is the radius and the change in pressure. We have a change in pressure of the first section. We simply need to isolate this variable right here. So we have delta P sub 2 equals delta P sub 1 times R sub 1 to the fourth over R sub 2 to the fourth. We can make it a bit simpler and say that the change in pressure in the first section times R sub 1 divided by R sub 2 all to the fourth power. At this point, we can simply substitute. So we have our P sub 1 is going to be 6 times 10 to the fourth pascals, and then times 0.210 meters divided by 0.07 meters, and that's going to give us to the fourth power, and that'll give us the pressure difference needed for the second section of this pipe. And we find that 0.21 divided by 0.07 is 3. 3 to the fourth power is going to be 81, and 81 times 6 times 10 to the fourth, we've come to 4.86 times 10 to the 6 pascals. So this would be the pressure difference needed in order for this volumetric flow rate to be maintained. And that's the end of the solution. Thank you for watching.